the 1940s and 50s, a new era in science was dawning, the nuclear age. Scientists at Oak Ridge National Laboratories in the United States were working furiously to unlock the secrets of extracting energy from the atomic nucleus, both for constructive purposes like the production of energy, and for more destructive endeavors also, like the race to develop an atomic weapon. Later in this course, we'll investigate the process of how atomic nuclei can be split and fused together to produce massive quantities of energy, both to the betterment and to the peril of mankind. But I need to invoke this compelling story now, because to reach the ultimate goal of creating a fuel suitable for reactors and explosives that harness the power of the atom, scientists first had to find a way to separate isotopes of the same element, namely uranium. Uranium is normally found in nature as a constituent of complex minerals. But when isolated and properly enriched in the correct isotopes, it can form a solid material used in fuel rods for nuclear reactors, or even the principal payload of certain nuclear weapons. Now remember that the atoms of elements can have different masses because of the number of neutrons in the nucleus, so that can vary. Uranium exists naturally as two main isotopes, 238 and 235. Naturally occurring uranium is more than 99% uranium-238, but this more stable isotope is not as useful as its lighter sibling. Fuels needed for nuclear reactors have to be at least 20% uranium-235, and those for use in weapons technology have to be at least 85% of this lighter isotope. Scientists at Oak Ridge had to isotopically enrich natural uranium into its 235 isotope, and that was no small task. We'll discuss the reasons for all of this in our nuclear chemistry lectures. But for now, let's focus on the problem which was facing the engineers at Oak Ridge in the 1940s. How do you separate two isotopes of an element that are so close to one another in mass and essentially identical in their chemical properties? Well, the researchers at Oak Ridge had their work cut out for them, and they found a solution for the enrichment of this solid material in the most unlikely of techniques, one involving the separation of gases, a technique called effusion. Now, gases tend to be pretty well-behaved substances, and we can formulate laws that describe them well based on the so-called ideal behavior. Laws like Boyle's, Charles', Gay-Lussac's, and even the combined and ideal gas law can be used to approximate the behavior of just about any gas or mixture of gases that we can imagine. But last time we stopped short of discussing exactly why we're able to come up with these all-encompassing gas laws. They seem to apply very well to a vast array of gaseous materials. You might recall from our discussion on the phases of matter that gases form when the atoms or molecules in a substance have sufficient kinetic energy to overcome the attractions that these particles naturally have for one another. When this happens, the gas particles have free run of their container, moving in random directions, independently and at great distances from one another, at least on the molecular scale. These remarkably consistent behaviors stem from the fact that most gas molecules are extremely small, move extremely fast, and do not interact with one another, or at least any interactions are negligible because of their speed. So it's this ideal behavior in the gas phase that makes the behavior of gases so predictable. So gas particles are moving fast. But how fast? And what factors affect their speed? Well, the answer to that question depends on a few factors. Let's start by considering just one gas particle. If I could isolate it in a container, it might look something like this: a randomly moving particle with a constant velocity. But we rarely, if ever, encounter a lone gas molecule in nature or in the lab. We usually run into them in huge groups, moles of atoms and molecules. So how do we account for this when it comes to how gases move? Now, to describe the energy contained in a single gas molecule, we could use the same type of equation that a physicist or engineer would use for an object. Right? E equals 1/2 mv squared. Now, when we arrange this equation a bit, we see that the velocity of the particle is a function of its kinetic energy and its mass. More accurately, the square root of the kinetic energy and the reciprocal of the square root of its mass. So the linchpin of this idea of kinetic molecular theory is that molecules are in motion, especially in the gas phase. So let's assume that we have a sample of gas phase molecules. Now I've just shown a container here in blue, and I've drawn my gas molecules represented here just as a red circle. But they don't look like this. They look like this, right? In real life, those gas molecules are in motion. They're constantly moving in random directions. They're colliding with each other, they're spinning, they're colliding with the walls of their container. But notice that they're not all moving at exactly the same speed either. Although there's probably sort of an average sense of how fast they're moving, if you look closely, you'll notice there's one right here that's moving a little bit slower than the rest. And if we look a little bit closer, we'll find, oh, here's one that's moving faster than the rest. So the motion of the molecules in the gas phase sample is somewhat random, but it's distributed statistically. So we report upon this speed as what we call an RMS velocity. Now the RMS velocity of a gas looks something like this for a sample, where the number of molecules is represented by the vertical axis at a particular speed represented by its position here along the horizontal axis. So the RMS velocity is right about here on a diagram like this, just slightly off from the maximum of the plot. So the RMS velocity is just slightly faster than the highest population, but it's a statistical average. So keep that in mind now. All these molecules that we talk about, we'll be talking about their RMS velocity in a sample, which only represents the average, not necessarily every single molecule. Now, we also know that the temperature of a gas is just a reflection of the kinetic energy that its molecules carry. So this leads us to the conclusion that the velocity of a gas molecule depends on two things: its temperature and its molecular weight. So let's begin to absorb this idea by observing the same exact gas at different temperature. We're essentially removing the influence of molecular mass and just observing the influence of temperature here. Well, we've already taken a look at a gas sample in motion. I've frozen it here for the moment because I want to heat one of these up. Let's increase the temperature and think about what that means for a molecule. That means more kinetic energy. What that means is that when I put these in motion, you can clearly see that the molecules in my heated sample are moving much faster, still randomly, still in a statistical distribution of velocities, but clearly much faster here than over here. So there's a relationship between RMS velocity and temperature, and we can determine that relationship mathematically, and we have. In fact, that relationship is this: the RMS velocity is proportional to the square root of the absolute temperature. So if I quadruple the absolute temperature, that means that I will double the RMS velocity of a gas sample. So what that means as far as my plots means this: if I have a gas that has an RMS velocity that looks about like this at 100 Kelvin, I can expect to have to heat it not to 200, not to 300, but all the way to 400 kelvins before that RMS velocity is doubled. This is our square root relationship. This relationship sets us on our way to coming up with a calculation that describes the average motions of gases in a useful way. It's the beginning, but it's not the end. Remember that to make our comparisons between temperature and RMS velocity, we had to set the stipulation that the molecular mass of the two gas samples were identical. This is simple when the two samples are the same gas, but what if they're not? We need to account for the effect of molecular mass, obviously. So to do this, let's flip the coin and keep the temperature constant so that we can study the effect of mass on RMS velocity. For example here, let's take a look at two different gases. In this case, I'll set them in motion. We have a less massive gas, something lighter, and we have a more massive gas, something that's got a greater molar mass at the same temperature. Now remember, temperature is all about kinetic energy. And if something has less mass, to get the same amount of kinetic energy, it must move faster on average, obviously. So my lighter weight gas is actually moving faster than the heavier one is. So there is a relationship between the molar mass of a gas particle and its RMS velocity. And the relationship is also a square root, but this time it's 1 over the square root of the molar mass. So this is our relationship that allows us to predict how fast things will be moving based upon their molar mass. In terms of our RMS velocity plots, that looks like this. Let's assume we're at a steady temperature now, 300 Kelvin, so we're not altering the temperature. This time we're going to look at the plot for various gases whose molecular mass we know. Take a look at these four. So these four plots would correspond to gases of varying mass. Right? Specifically, these RMS velocities would correspond to something like oxygen up here at 32 grams per mole having the lowest, water at 18 grams per mole being a little bit higher, helium at 4 grams per mole even faster, and H2 at just 2 grams per mole being the fastest of all. And just like with temperature here, the relationship is a square root relationship. So we have to cut the mass by a factor of 4 to increase the RMS velocity by a factor of 2. So we now understand not just qualitatively, but quantitatively how the temperature and the molar mass of gas samples affects their RMS velocity. But again, we have to ask ourselves, to what end? Our discussions of kinetic molecular theory so far have netted us two very important relationships. They've led to the conclusion that the RMS velocity is proportional to the square root of temperature for a sample, and also that the RMS velocity is proportional to 1 over the square root of the molar mass for a sample. But these are still just proportionalities. How do we get to an equality? How do we get to something that we can really use mathematically? Well, we have to combine those two proportionalities for starters. Realize that the RMS velocity is proportional to the square root of the temperature over the square root of the molar mass for any gas at any temperature. Now, when we do this and run a few experiments, we can determine that proportionality constant. And the proportionality constant is the square root of 3 times R, the ideal gas constant, which leads to an equation where we can get the actual RMS velocity. It's equal to the square root of 3 times the ideal gas constant times the absolute temperature of the sample divided by the molar mass of that sample. Now, using that equation, we can actually determine what that RMS velocity is for a given gas at a given temperature. So let's do that. Let's calculate the RMS velocity of a nitrogen molecule at about room temperature, 298 kelvins. Let's see how fast those molecules are really going on average. First thing we're going to do is calculate the molar mass of N2, remembering that it is a diatomic molecule. The periodic table lets me know that the molar mass of nitrogen atom is 14.007, so I'm going to make it 28.014 because this is 2 nitrogen atoms bonded together. Now we'll calculate the RMS velocity at this given temperature here of 298 kelvins. We have the square root of 3 times the ideal gas constant in some units that we're not used to seeing very often, but I assure you this is still the exact same value as the ideal gas constant we're used to seeing. It's just that we've used different units to be sure that our unit analysis works correctly. We're going to multiply that value by the temperature that we'd like to know, and of course divide through by our molar mass, 28.014 grams per mole. Now that's a big equation, but it still is going to have to be checked by unit analysis. Let's do it. Grams cancel. Moles also cancel. Even kelvins will cancel, leaving me with meters squared per second squared. But remember, the expression is underneath of a square root, so that's going to cancel out the squares. I get exactly what I need, meters per second. That is a velocity unit. So running my calculation leads to the following answer. 515 meters per second. That means that the average nitrogen molecule at room temperature, like the ones that are in the room you're in right now, is moving at about the same speed as the muzzle velocity of a 9mm bullet. That is a staggering speed, isn't it? Proof of the impressive speed of gas particles, and also a simple explanation of how your buddy's slightly excessive application of cologne can clear a party out in just about no time. The molecules putting off that insufferable scent can literally move as fast as a bullet and metaphorically kill a party with equal efficiency. It's this predictable behavior of gases, higher RMS velocities for those with lower molar masses, that really caught the interest of those researchers at Oak Ridge National Lab. To better understand why they found this so interesting, we have to first explore a fundamental gas law that we have not yet considered: Graham's law of effusion. Remember that when we compared several gases near room temperature, or 25 degrees centigrade, we saw a trend in the RMS velocity. Of course, this should come as no surprise because our equation describing the energy of a sample has a term for mass. So at a given temperature, Heavier particles, on average, will move more slowly. Scottish researcher Thomas Graham put this notion to the test when inspired by a colleague's observation that helium escaped a leaking container faster than the atmosphere found its way back in to replace it. That's an interesting observation, isn't it? Very small helium atoms seem to escape their container faster than molecular oxygen and nitrogen, each about 8 times more massive, can find their way in. Now, the process of gas escaping its container through the walls is known as effusion. Graham immediately noticed a strong relationship between the molecular mass of a sample and the speed with which it could escape by this process. So here I've got a sample of gas inside of a container, but I've introduced some little pores here. Now, I want to make this very clear. Gas molecules are extraordinarily small in comparison to the size of even the tiniest pore that you might find. So although they may look of similar size here, keep that in mind in my animation here, that these gas particles are very, very, very tiny. So to get out through a hole, all they have to do is randomly find that opening. But of course, right now my gas is at absolute zero, right? It's not moving. Let's put it up to a more realistic temperature. Let's get this thing in motion like a real gas would behave. Now you notice again, my gas molecules are in random motion, bouncing off of one another in the walls of the container. But occasionally one of them finds that opening and is able to escape. And once it escapes, it's gone. So as my molecules are moving in this random walk through the container, sooner or later they're going to find that pore and they're going to make their way out. And if I wait long enough, the process of effusion is good enough to essentially get my entire sample of gas to escape. Now, where this comes to bear on what Graham saw is this. Consider that gases of varying sizes are known to have different RMS velocities. Specifically, lighter gases are going to have a higher RMS velocity. And what this means is if I start my gas molecules in motion here, that my faster moving gas sample, notice it's having more collisions with the wall, which means it has more opportunities to randomly find the opening and exit. In fact, in the amount of time it's taken me to explain that to you, we've lost basically all of it. Now, in the meantime, on the other side, my larger, slower moving gas is effusing for sure, but it's doing so at a much lower rate because its slower RMS velocity means that the compounds or the molecules making it up have less opportunity to collide with the wall and randomly find the opening. But again, if I wait long enough, I can get essentially all of my sample to escape. Graham set to measuring the rate at which gases escaped vessels through porous materials like plaster. Now, not only that, but the correlation was mathematical, and it suggested that average particle speed was the driving force. Let's derive Graham's law. Now, Graham's law of effusion is based upon some mathematical relationships we already know. The RMS velocity of a gas is proportional to 1 over its molar mass at a given temperature. But the rate of effusion is also proportional to the velocity. The faster they move, the more chances gas molecules have to escape. So rate is proportional as well to the RMS velocity, meaning rate itself is proportional to 1 over the square root of the molar mass. Well, this is true for any gas that's ideal. So the RMS velocity of a second gas is also proportional to 1 over its molar mass, which means the rate is also proportional to 1 over the square root of its molar mass. And again, I have two proportionalities. How do I turn them into an equality that I can use? I divide one through by the other. So by placing my first proportionality over my second, I have an equality. Right? The ratio of rates is equal to 1 over the square root of the molar mass of the first divided by 1 over the square root of the molar mass of the second. That's a lot of 1 overs, isn't it? So let's simplify just a little bit here by using a mathematical trick. We're going to flip those terms over. Now we have what's known as Graham's law of effusion. The relative rates of effusion of two gases is proportional to the square root of the ratio of those two gases' molar masses. So let's put Graham's law into action and do a calculation. We'll calculate the relative effusion rates of two very familiar gases, hydrogen and oxygen. Now, in order to do this, we need to know the molar masses of both, and those are easily obtained from the periodic table, remembering these are diatomic molecules. So the molar mass of H2 comes out to 2.016. The molar mass of O2 comes out to 31.998. I'm going to place those numbers into my Graham's law calculation. And just to keep things a little bit simpler, we're going to round these to their nearest whole number, 32 over 2. So, because the oxygen is 16 times more massive, the rate of effusion is going to be the square root of 16 times slower. In other words, a difference of a factor of 4. We expect hydrogen gas to effuse 4 times faster than oxygen gas at any given temperature. So why does Graham's law work so well? The answer to this question lies in our original assumptions about ideal gases. Remember, we assume that gas particles are extremely small and moving in random walks independently of one another. If we add that to our new concept from today, the RMS velocity of a gas being a function of the mass of the gas particle, it begins to become clear what's happening here. Faster moving gases have a better chance of finding the opening more quickly, causing them to effuse faster. If a gas moves twice as fast, it should escape the container twice as fast also. Graham's law relating molecular mass to effusion rate was a profound realization because it allows us to intelligently construct facilities that can separate gases based on little more than a difference in their molecular masses. Now let's take one more look at the process of effusion. But this time, let's add some smart design to our container and see if we can isolate one gas from another. The technique that allowed scientists in Tennessee to actually isolate molecules of uranium hexafluoride is based upon all the same phenomena we just discussed. Imagine, if you will, a container that has 2 different gases mixed together, one slightly heavier than the other. And I'm going to set these in motion. But not only that, I'm going to put walls in between these, creating chambers. But those walls are going to have permeations in them, small pores. So now the gases are able to effuse from one chamber to the next. But because their RMS velocities are slightly different, the rate at which they do so is also slightly different. And if I catch the other end of my apparatus here at just the right time, look what's happened. I've actually got an enriched sample of the lighter gas. So this effusion method of collecting very slightly lighter gases is what was originally used to obtain the fuel needed to create the very first nuclear bomb. So let's go back to our original story now. The quest for isotopically enriched uranium-235. Graham's law of effusion tells us that if we can get uranium into the gas phase, we should have 2 types of gas particles, one having uranium-235 and the other having 238. But uranium isn't a gas. So why did we just spend most of our lecture discussing gas effusion in a quest to understand uranium enrichment? Well, because this is actually the technique that was used in the 1940s and 50s to acquire the material needed for nuclear devices. Government scientists had developed a way to make a gaseous material from uranium by reacting it with fluorine gas to produce uranium hexafluoride. Let's apply a bit of our chemical knowledge to this molecule to try to understand why this worked. Uranium hexafluoride is an octahedral compound with an AX6E0 formula. This means that it has an octahedral geometry which results in a cancellation of the uranium-fluorine bond dipoles. This molecule is nonpolar. No molecular dipole-dipole attractive forces are going to be happening here. But it's so large. Why aren't dispersion forces powerful enough to make it a solid, or at least a liquid? Well, because the geometry of the molecule surrounds the huge polarizable uranium electron cloud with tiny fluorine electron clouds. So the face of this molecule actually contains a much less polarizable cloud than uranium itself would. These factors combined mean that uranium hexafluoride boils at a remarkably low temperature of just 57 degrees centigrade, or 133 Fahrenheit. Remarkable when you consider that pure uranium metal doesn't even melt until it reaches 1,132 degrees centigrade, or over 2,000 degrees. And that's just melting. To get pure uranium into the gas phase requires over 4,000 centigrade, about half as hot as the surface of the sun. But that isn't the only reason fluorine was used for this process. Not only does it react with uranium to produce a volatile compound, but fluorine itself is special. because it's one of just a handful of elements that forms only one natural isotope, in this case fluorine-19. This means that any difference in the mass from one molecule of UF6 to the next must be the result of the uranium atom entombed inside. So only two potential UF6 molecules can form, one weighing 349 atomic mass units and another weighing 352 atomic mass units. If we use these molecular masses in the Graham's law calculation, we can see that lighter uranium-235 containing molecules of UF6 should diffuse 0.4% faster than the heavier U-238 containing molecules. Not quite as staggering a difference as with oxygen and hydrogen, but in this case, that frustration was worth dealing with, because enriched uranium was the key to a device that could put a swift end to the deadliest war in the history of the world. K-25 in Tennessee was a monolithic facility. It stretched a half a mile with a footprint covering an area larger than the Pentagon. It consisted of chamber after chamber, each divided by sintered aluminum barriers with pores just a dozen or so nanometers wide, just large enough that the effusion rates would be practical for this application. As freshly prepared UF6 gas effused from one chamber into the next, it would continually be enriched in U-235, 0.4% per chamber. After thousands and thousands of cascades through the building, the UF6 at the opposite end could be harvested and the uranium collected for use in the intended application. This method remained a viable means of enriching uranium for many decades, with K-25 operating until 1987, producing weapons-grade uranium for the U.S. Cold War arsenal, and later in its life, less enriched, but no less critical, fuel for nuclear reactors around the world. So this vapor effusion method of enrichment was critical to the development of technologies that not only brought World War II in the Pacific Theater to its historically abrupt end, but that helped power the homes and businesses of millions. And that's how the clever application of Graham's law launched the nuclear age, by providing a way to get isotopically enriched material needed for these kinds of applications. Probably not what Graham had in mind when he started investigating a leaky helium tank a century earlier, but an impressive accomplishment nonetheless. So let's sum up our discussion. Today we discussed kinetic molecular theory. We explored the kinetic energy of gaseous materials and how the molecules that comprise them each act like very small moving bodies in physics. Then we considered how to treat a gas sample as a whole, which is a huge collection of independently moving particles. We discussed the concept of average energy and RMS velocity, and we saw how both of these properties are dependent on the temperature of the sample and the molar mass of the gas particles. Next, we met Thomas Graham, whose experiments in gas effusion reinforced kinetic molecular theory and also gave us a mathematical relationship between relative rates of effusion and the molar mass of a gas. Finally, we saw how Graham's law was employed by an ambitious military project in the 1940s in America to obtain the nuclear fuel that they needed to produce one of the world's most powerful weapons, altering the course of human history. So, by now, I hope that you agree. The behavior of gases at the atomic and molecular level is something worth understanding. Its knowledge so powerful that it can provide fuel for nuclear reactors and even a payload for a devastating weapon. If so, that's great, because it's time for us to press ahead. Next time, we're going to take a look at the liquid phase of matter and how substances in that phase behave.